Hello, I'm Benjamin Kurian, and this is a video on existence of a convergent subsequence for a sequence of functions. We know in the set of complex numbers, every bounded sequence has a convergent subsequence. Also, every subsequence of a convergent sequence is convergent. Hence, here, in the set of all complex numbers, given a sequence xn, the existence of a convergent subsequence is ensured if xn is bounded or if xn is convergent. So, one might think what conditions are needed for a sequence of functions fn of x on E to have a convergent subsequence. Does it depend on the selected set E, whether it is a finite set or a countable set or a compact set? Does it depend on the convergence of fn of x? If yes, which kind of convergence? Pointwise or uniform? And most importantly, does it depend on the boundedness of fn of x? Now, what do we mean by boundedness for a sequence of functions? A sequence of functions fn of x on E is said to be pointwise bounded if for any point x in E, the corresponding sequence fn of x is bounded. That is, corresponding to every x belongs to E, there exists a finite number m of x, such that mod of fn of x is less than mx for all n belongs to natural numbers. Let's see this through an example. Consider the sequence of functions defined by fn of x equal to n when x is between 0 to 1 by n and 0 otherwise. Here, fn is a pointwise bounded sequence of functions in R. How? Well, let's see its graph. This is how fn of x looks like for n equal to 1, 2, 3, 4, and so on. Now, we fix a particular point x, the red dot that you see on the x-axis, and then observe the corresponding fn of x represented by the orange dot on the curve. Following this value of fn of x or the orange dot for n equal to 1, 2, 3, 4, and so on, we see that the orange dot first rises, reaches some maximum height, and then drops down to the x-axis and remain there. This implies that for any particular point x, as n increases, the value of fn of x first increases, attains a maximum value, and then drops down. That is, there is a maximum value of fn of x, and fnx will never go beyond this point, no matter how big n is. This is what we mean by pointwise boundedness. It says for any particular point x, the set of values of fnx as n tends to infinity is bounded. Also, it can be clearly seen by the animation here that as the value of n increases, the graph of fnx tends towards the 0 function. This means that fn here converges to f pointwise, or limit n tends to infinity, fn of x is equal to f, where f is the 0 function. What interests me the most about this given sequence of functions is the integral values of fnx for each n belongs to natural numbers. When n equal to 1, integral f1x dx is the area under the curve, which we can see here is the area of the square of unit length, which implies integral f1x dx is nothing but 1. Similarly, for n equal to 2, integral of f2x dx is the area under this rectangle with base length half and height 2, which implies integral f2x dx is again half into 2 equal to 1. For n equal to 3, integral f3x dx is the area under this rectangle with base 1/3 and height 3, which again implies integral f3x dx is 1 by 3 into 3 equal to 1. Hence we see that for any n belongs to natural numbers, the integral of fnx dx is equal to 1. That is, even though the curve of fnx tends towards the 0 function, where 0 function has the integral 0, the area under the curve somehow remains constant and clearly greater than 0 for any n. We shall come back to this result later. Moving on. A sequence of functions Fn on E is said to be uniformly bounded on E if the set of all possible values of Fnx is a bounded set. That is, there exists a fixed finite number m such that mod of Fnx is less than m for all n belongs to natural numbers and for all x belongs to E. Let's look at an example. Consider the sequence of functions defined as Fnx equal to sine of nx, where x belongs to 0 to 2 pi. Then, Fn here is a uniformly bounded sequence. To visualize this, we look at the graph of Fnx. This is how Fnx looks like for n equal to 1, 2, 3, 4, and so on. Now, we take any random collection of points on the interval 0 to 2 pi, which is represented here by the blue dots that you see on the x-axis, and then observe the corresponding Fnx, represented by the red dots that you see on the curve. Following these values of Fnx or the red dots for n equal to 1, 2, 3, 4, and so on, we see that no matter how big n is, and no matter what my point is, the set of all possible Fnx values is bounded or contained inside a fixed interval. This is what we mean by uniform boundedness for a sequence of functions. Also, note that Fnx equal to sine nx is a continuous sequence of functions, or a sequence of continuous functions. Since sine x is continuous, sine 2x is continuous, and so on. Hence we say that Fn here is a uniformly bounded sequence of continuous functions on the compact set 0 to 2 pi. Now that we have the idea of boundedness, we can go back to our primary discussion. That is, does the existence of a convergent subsequence of Fnx depend on boundedness? And if yes, which type of boundedness? Pointwise or uniform? It is important to note that here, when we say that a subsequence Fnk of x is convergent, we usually mean that Fnk is pointwise convergent, and it may or may not be uniformly convergent. Let us start with a question. Given a sequence of functions Fn of x on E, if Fn converges pointwise to some function f on E, then can we say that limit n tends to infinity, integral over E Fn of x dx is equal to integral of E limit n tends to infinity Fn of x dx? That is, can limit freely move inside and outside the integral? The answer is a big no. Consider our previous example where Fn of x is equal to n, 0 less than or equal to x less than or equal to 1 by n, and 0 elsewhere. Here Fnx converges pointwise to the 0 function, so that the integral of the limiting function f, 0 function, becomes 0. But as we saw earlier that the integral value of Fn of x for any n belongs to natural number is 1, so that the limit as n tends to infinity of those integrals become 1, hence justifying our big no. It is important to note here that if the sequence Fn of x converges to fx not only pointwise but also uniformly on E, then we can directly say that this equality holds. So, let's change our question. Given a sequence of functions is pointwise convergent, which may or may not be uniformly convergent, when can we say that the limit of integral values of Fnx on E is equal to the integral of the limiting function on E? Here we introduce the dominated convergence theorem, or the Lebesgue dominated convergence theorem, which states that given a sequence of functions Fn of x on a measurable set E, such that Fn of x converges pointwise for all x in E, then if there exists some function gx belongs to L mu, that is, if we can find a Lebesgue integrable or an integrable function gx on E such that the values of mod of Fnx is bounded or restricted or dominated by the value of gx for every n belongs to natural number and for all x belongs to E, then we can say that the equality holds. Let me describe this visually. The theorem states that given a sequence of curves f and x on E, if f and x tends to a fixed curve fx on E, and moreover, if we can find another fixed curve g of x which dominates over all the values of mod of f and x as n tends to infinity, and the integral of gx is finite, then we can say that the area under the curves of f and x tends to the area under the curve of fx as n tends to infinity. Now let's take a 10-second break. Now, our primary goal, which was to see how the existence of a convergent subsequence for a sequence of functions is related to the nature of the sequence of functions taken. So keeping all that in our mind, let's move on to the next part of this video. Remember the graph of the sequence of functions sin nx? Note that here the curves of the sequence of functions f and x does not converge or tend towards a fixed curve. That is, the values of f and x for some fixed x belongs to 2 pi keeps on oscillating as n tends to infinity and never rests to a single point. Hence, fn here is not a pointwise convergent sequence of functions. The question is, from here, can we directly infer that the sequence of functions sin nx will never have a convergent subsequence? The answer is, well, we don't know yet. But what we do know is that in the set of complex numbers, even if a sequence xn is divergent as long as it's bounded, one can find a convergent subsequence. So here, for fnx equal to sin nx, we know fn is not a convergent sequence of functions, but we did see earlier that fnx is a uniformly bounded sequence of continuous functions. Let, if possible, fn of x have a convergent subsequence of functions, say fnk of x. Then, for a fixed x belongs to 0 to 2 pi, limit k tends to infinity, fnk of x exists and is obviously same as limit k tends to infinity fnk plus 1 x, since nk tends to infinity and nk plus 1 tends to infinity are equivalent statements. Hence, we can say for all x belongs to 0 to 2 pi, the difference limit k tends to infinity fnk of x minus limit k tends to infinity fnk plus 1 x is equal to 0, where by definition the subsequence of functions fnk of x corresponds to sin nkx, x belongs to 0 to 2 pi. From here, it can be easily derived that limit k tends to infinity in sine of nkx minus sine of nk plus 1 x, the whole square, is equal to 0, holds for all x belongs to 0 to 2 pi. What this means is, for the sequence of functions defined by hkx equal to sin nkx minus sin nk plus 1x, the whole square, x belongs to 0 to 2 pi, is a sequence of functions that converges pointwise to the 0 function hx equal to 0, x belongs to 0 to 2 pi, as k tends to infinity. Now, by looking at its graph, we can find many dominating integrable functions. One such function being gx equal to phi, the number phi, for all x belongs to 0 to 2 pi, such that the values of mod of f and x is always less than the value of gx for all n belongs to natural number and for all x belongs to 0 to 2 pi. Note that here a dominating function gx must be independent of n and integrable on the interval. Hence, by applying the Lebesgue dominated convergence theorem for the sequence of functions hk of x on the compact set 0 to 2 pi, we get limit k tends to infinity integral of h and k of x dx is equal to integral of the limiting function, which here is the 0 function, on the interval 0 to 2 pi. Hence, we get limit k tends to infinity integral 0 to 2 pi sin nkx minus sin nk plus 1x the whole square dx is equal to integral of 0, which is 0. But as it turns out, for any fixed k belongs to natural numbers, considering nk and nk plus 1 as constants, through simple integration, one can derive that integral value of sin nkx minus sin nk plus 1x the whole square on 0 to 2 pi is always equal to 2 pi, which would then mean that the limit of these integrals, limit n tends to infinity, integral 0 to 2 pi sin nkx minus sin nk plus 1x the whole square is in fact not equal to 0 but equal to 2 pi, which is a contradiction. Hence, we can now say that our assumption was wrong. That is, there does not exist a convergent subsequence to the given sequence of functions sin nx. X belongs to 0 to 2 pi. What we can conclude from here is that given a sequence of functions fn on E, even if the set E is compact and fn is uniformly bounded on E, it does not necessarily mean that there exists a pointwise convergent subsequence of functions. Let's take a 10-second break. Let us start by observing the sequence of discontinuous functions f1x, f2x, f3x, and so on. Does this converge? The answer is yes. As we can see here, this discontinuous sequence of functions converge pointwise to the continuous function sin of x as n tends to infinity. Now, is this convergence uniform? By definition, we have the statement a sequence of functions fn of x converges uniformly to f on E if and only if for all epsilon greater than 0 there exists one natural number capital N such that mod of fnx minus fx is always less than epsilon for all small n greater than equal to capital N and for all x belongs to E. Hence, as a negation to this statement, we can say a sequence of functions fnx does not converge uniformly to f on E if and only if there exists at least one epsilon greater than 0 such that for any n belongs to natural numbers, the value mod of fnx minus fx is greater than equal to epsilon for some x belongs to E and n greater than equal to n, capital N. Note that here, when we negate the statement, we not only reverse the main condition, that is mod of fnx minus fx is less than epsilon, but we also interchange all the for alls with there exists and all the there exists with for alls, which, if you think about it, makes complete sense. Let's visualize these two statements graphically. We say that the sequence of curves fnx uniformly converges to its limiting function fx if and only if, no matter how small epsilon neighborhood represented here by the cylindrical pipe around our limit function sin x that we take, one can always find a particular f capital Nx curve in the given sequence of functions such that all curves beyond or succeeding this curve lie completely inside this pipe and never jump out for any x belongs to E. On the contrary, consider the sequence of functions defined by fn of x equal to x square divided by x square plus 1 minus nx the whole square. This is how this sequence of curves look like graphically for n equal to 1, 2, 3, 4, and so on. Since for any fixed point x in 0 to 1, the value fnx first rises, reaches a fixed maximum height. Remember, a fixed maximum height of one unit, but then ultimately settle down on the x-axis. So we can say that this sequence of functions converge pointwise to the zero function. Also, we can say that all the f(n)x curves are continuous curves, and the set of all possible values of f(n)x for any n is throughout or uniformly bounded on 0 to 1. Adding all this up, f(n)x here is a uniformly bounded, pointwise convergent sequence of continuous functions on the compact set closed interval 0 to 1. But here we can find many epsilon neighborhoods, one such being the epsilon equal to half neighborhood of our limiting curve, the zero function, such that for every n belongs to natural numbers, we can always find some point represented by the red dot on the curve that remains outside, almost as a rebel of the epsilon equal to half neighborhood of the limiting function. This is nothing but the negation of the statement for uniform convergence. Hence, f(n)x here and consequently any subsequence of f(n)x will not be uniformly convergent. How? Well, since for a subsequence of functions f(n)k of x, for any nk belongs to natural numbers, the f(n)kx curve will again have the rebel red point completely outside the fixed epsilon equal to half neighborhood of the limiting zero function. What we can conclude from here is that given a sequence of functions f(n)x on E, even if E is compact, Fn is uniformly bounded and Fn is convergent, it still cannot have a uniformly convergent subsequence if the convergence of the given sequence is not uniform. So to sum up, in this video we have successfully explored a bit of how the existence of a pointwise or uniformly convergent subsequence depend on the boundedness and then the convergence of the given sequence of functions. In the next video, it will be proved that if E is a countable set and the given sequence is pointwise bounded, then it will 100% have a convergent subsequence. The link to the notes used here in this video is given below in the description, along with the link to all the graphs that you saw. I would highly recommend you to check out all these graphs and using just that, find an answer to the following 3 questions. Thanks for watching. Bye.